Imagine you are an engineer standing in a workshop during the early days of electricity. You have batteries, copper wires, and light bulbs. You know that if you connect them in certain ways, the lights turn on. But you do not have Ohm's law. You do not have a fundamental equation that predicts exactly how much current will flow for a given voltage. You are relying on trial and error. You tweak the connections, you burn out a few components, and slowly you build a sense of what works. That is exactly where the field of deep learning finds itself today. We have powerful neural networks that can recognize faces, write code, and translate languages, but we often treat them like magic boxes. We adjust the knobs, we hope for the best, and we pray the model generalizes to new data. Here is the thing. We are on the verge of a massive shift. Recent scholarship suggests that deep learning is transitioning from a heuristic discipline into one grounded in a unified scientific theory. This is not just about knowing that a model works. It is about understanding the underlying mechanics that dictate why it works. The emerging framework is often referred to as learning mechanics. It posits that training dynamics and performance can be characterized through coarse aggregate statistics and falsifiable predictions, much like physics rather than biology. This perspective draws on several converging strands of research, including solvable idealized settings and tractable limits. It suggests that there are simple macroscopic laws governing how these systems evolve. Now consider the practical implication for someone building production systems. If deep learning is moving toward a physics-like theory, then debugging a failing model should not be a guessing game. It should be a diagnostic process based on physical principles. One of the most significant insights coming from this new theoretical landscape involves the relationship between depth and width. Research by scholars like Roberts and colleagues supports an effective theory where depth-to-width ratios govern deviations from Gaussian behavior. They utilize a concept called renormalization group flow to explain signal propagation and criticality. In simpler terms, this means the way information flows through your network depends heavily on the geometric proportions of your architecture. If you are designing a neural network for a production environment, this changes how you approach initialization and architecture selection. Instead of arbitrarily choosing a number of layers or neurons, you are now looking for a regime of operation. You want to ensure that the signal propagates correctly from the input layer to the output layer without vanishing or exploding. This is a criticality condition. If your network is too shallow, it might not have the representational capacity. If it is too wide without enough depth, it might fail to learn hierarchical features. The theory tells us that there is a sweet spot, a critical point, where the system is most efficient at learning. This brings us to the concept of universal behaviors. The idea is that diverse system architectures might share underlying statistical properties. Just as water behaves similarly whether it is in a glass or a river, neural networks might exhibit universal behaviors during training. This suggests that we can develop debugging heuristics that apply across different tasks. For example, if you observe a specific pattern in the loss landscape or the gradient norms, it might indicate that you are far from the critical regime. You might not need to retrain the model for weeks. You might simply need to adjust the learning rate or the initialization scheme to bring the system back to that critical point. However, we must be careful not to overstate our current capabilities. While there is strong consensus that a fundamental theory is both feasible and necessary to move beyond trial and error, the field currently lacks a complete synthesis of these distinct approaches. Significant knowledge gaps remain in integrating mechanistic interpretability with these macroscopic laws. We are still trying to fully quantify the universal behaviors across diverse system architectures. The primary challenge lies in bridging the gap between abstract mathematical limits and the complex, finite realities of practical neural network training. Think of it like the difference between a perfect vacuum in a physics textbook and the messy reality of a laboratory. The theory provides the idealized setting. The production environment provides the noise, the limited data, and the computational constraints. Future research aims to overcome this hurdle through a proposed symbiotic relationship between statistical, information, theoretic, and mechanical perspectives. This means we will eventually have tools that combine the rigor of mathematics with the pragmatism of engineering. For the practitioner listening, the takeaway is to shift your mindset. Stop thinking of your neural network as a black box that you tune by intuition. Start thinking of it as a dynamical system. When you encounter a performance drop, ask questions about the signal propagation. Ask questions about the depth-to-width ratio. Ask if the network is operating in a regime where it can actually learn the task at hand. This is the shift from purely empirical optimization to formal mathematical proofs that characterize the why behind deep learning phenomena. The ultimate goal is a theory of everything for deep learning that unifies disparate concepts like overparameterization, implicit bias, and optimization landscapes into a coherent scientific model. It would explain why adding more parameters sometimes helps and sometimes hurts. It would explain why certain architectures generalize better than others. It would demystify the black box nature of modern artificial intelligence. We're moving towards a phenomenological approach where we can predict the behavior of hierarchical architectures and compressive data evolution without needing to train every single variant from scratch. This transition will not happen overnight. It requires a collective effort from the research community to validate these predictions and integrate them into standard development workflows. But the direction is clear. We are moving from a discipline of discovery to a discipline of understanding. By adopting these theoretical insights, we can build systems that are not just more accurate, but more reliable and interpretable. We are building the foundation for a future where we do not just know that a machine can learn, but we understand exactly how and why it learns. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.